students. So today we will be discussing about colligative property. So colligative property is the property of a dilute solution, okay, which depends upon the number of solid molecules present in a known volume of the solvent. It depends upon only the number of solid molecules present and not upon the nature of the solid present in the particular solvent. So in a way, this colligative property are those properties which depend upon only the number of solid molecules. Solid molecules, it could be ions, particles, okay? And this, whenever there is change in the number of ions or of the solid particles, then there are some variation in these properties. Okay, so just you have to remember, colligative property depends upon only the number of solid particles. So example of colligative properties are, you have relative lowering of vapor pressure, relative lowering of vapor pressure, and depression in freezing point, elevation in boiling point, elevation in boiling point, and also osmotic pressure. So these are some of the examples of colligative property. Okay, and all of them we are going to discuss one by one in more detail. And from this particular 4 examples, what will be asked is, you will be deriving the final expression, and that expression will be used to find the molecular mass of the solid or solvent molecule. Mostly it's the solid molecules. So colligative property, it means the property which depends only on the number of solid molecules. The properties which depends only on the number of solid particles. If there is change in the number of particles, then the properties will also change. Now let's discuss about the first topic, first example, that is the lowering of vapor pressure. That is, we have lowering of vapor pressure. Lowering of vapor pressure. So this we have discussed in our previous video also. So whenever we are adding a non-volatile solvent to a solvent, then the vapor pressure will be lowered by the addition of this non-volatile solid particle. We have discussed this. Why? Because these non-volatile solid molecules will occupy some of the areas of the surface area, and since they are not going to the vapor phase, therefore they are stored as what? They are stored as non-volatile. Now it will hinder in the evaporation process of the solvent molecules. Therefore, addition of non-volatile solid particles results in lowering of vapor pressure. Results in lowering of vapor pressure. So this can be known from Raoult's law. Okay, can be readily understood in terms of Raoult's law. So let's consider a solution. Let's consider a solution. We are considering a solution. A solution which is obtained by dissolving certain moles of this non-volatile solid molecules in certain moles of this liquid or the solid. So suppose we have, say, that solution will contain that x1 is the mole fraction, and x1 and x2 be the mole fraction of the solvent. X1 is for solvent and x2 is for what? Is the mole fraction of non-volatile solid molecule. Then we can know from this mole fraction formula, then x1 is given by what? X1 is given by number of moles of this is n, okay? That is x and this is n. X is the mole fraction and n is the number of moles of solvent divided by number of moles of solvent plus number of moles of solid particle, and x2, that is x2 is the mole fraction of the solid particle, is given by n2 divided by n1 plus n2. So the mole fraction can be known from the number of moles of the solid and the solvent molecule. Now, in this case, we can see that since the solid is non-volatile, therefore the contribution of this solid particle to the total vapor pressure is what? Negligible. Therefore, the vapor pressure of the solution is entirely nearly the vapor pressure of the solvent only. Okay, now from Robert's law we can know that so I told you the contribution of the moles of this non-volatile solid particle to the total vapor pressure is negligible. Therefore, the total vapor pressure of the solution is nearly equal to the vapor pressure of the solvent only. Therefore, from the Robert's law, the vapor pressure of the solvent, that is P, the vapor pressure of the solvent in solution will be equal to the vapor pressure in the pure state into mole fraction of the solvent molecule. Okay, this is x1 is the mole fraction of the solvent molecule, and p0 is the vapor pressure in the pure state of the solvent. Now, here we have to know that the total mole fraction, that is x1 plus x2, will always be equal to 1. That is the mole fraction of the solvent as well as the solid molecules. Mole fraction of the solvent and the solvent will always be equal to 1. And since here we can see that only the number of moles of solvent is involved in or contributing in the total vapor pressure of the solvent in the solution. Therefore, its vapor pressure is always slightly less than that of the pure solvent. Since x1 is always less than unity, P is less than P0. This P will be less than this P0. Okay, why? Because this is always less than 1. I told you why? Because this 2 will be equal to 1, and there are certain moles are also present, mole fraction is also present in solution. Therefore, If you multiply this, you will be the value that you get here. The P will be less than that of what? P naught. Okay? Now this proves that the addition of a non-volatile solid molecule in the solvent will always result in lowering of the vapor pressure. So we can write like this. Now, lowering of vapor pressure will be equal to what? Will be equal to, say, delta P. Now this delta P, how much of it is lower? How do we know it? We have to subtract this P from P naught. Okay? So P naught minus P. Now from this expression, we know that this P is equal to P naught x1. Therefore we can substitute this P with P naught x1. Now delta P will be equal to P naught 1 minus x1. Now this 1 minus x1, now 1 minus x1 will be equal to x2. Delta P will be equal to P naught x2. Therefore, see, lowering of vapor pressure is directly proportional to x2. x2 is what? x2 is the mole fraction of the solid molecule, non-volatile solid molecule. Please remember this. The more number of moles you add of this non-volatile solid particles in the solvent, then the lowering of vapor pressure will also be higher. Now, this expression can also be written as this delta P is equal to what? P naught minus P. Now this gave us which expression? P naught x2. Yes or no? Now if we divide all of this expression by P naught, what will we get? What will be getting? P naught by minus P by P naught will be equal to P naught x2 by P naught. Okay? Now this you will be getting as this P will cancel out x2. So you will be getting P naught minus P by P naught equals to x2. Now this term P naught minus P by P naught is known as what? Relative lowering of vapor pressure. This is known as what? Relative lowering of vapor pressure. And you can see that this relative lowering of vapor pressure is directly proportional to the mole fraction of what? 2 here. 2 is for solid, non-volatile solid. Please remember. Therefore, we were discussing about qualitative property. Please don't forget. So we can see that relative lowering of vapor pressure is directly proportional to the mole fraction of the solid, non-volatile solid particles. Therefore, this relative lowering of vapor pressure is a qualitative property. If you increase the mole fraction or the number of moles of solid particle, then the relative lowering of vapor pressure will also be hindered, either it increases or decreases. Here in this case, it will increase. More the number, more will be the relative lowering of vapor pressure. Okay, now here we can also see that we can replace this with mole fraction. This mole fraction is given by what? P naught minus P by P naught. Same thing here, this can be written as N2 divided by N1 plus N2. 2 is for solid, N1 is for what? Solid molecule. Now for a dilute solution, you know, for a dilute solution, the number of moles of solvent is such large compared to what? Number of mole of the solid particle. Therefore, we can neglect, since N1 is very large compared to N2. This N2 in the denominator can be neglected. Therefore, this expression can also be written as P0 minus P by P0 equals to N2 by N1. Okay? N2 by N1. Now, for a definite volume of a solvent, what is known? P0 is known and N1 is known. Therefore, this P0 minus P by P0 is again directly proportional to N2, because this, for a definite volume of a known solvent, this N1 and P is what? Known. It's a known quantity. Therefore, again we can see that it's a relative lowering of vapor pressure is directly proportional to the number of moles of what? Solid quantities. Therefore, this also proves that relative lowering of vapor pressure is a colligative property. Relative lowering of vapor pressure is what? Colligative property. Don't be confused. Okay? Relative lowering of vapor pressure is a colligative property, but only lowering of vapor pressure is not a colligative property. You have to keep this in your mind. Lowering of vapor pressure is not a colligative property. Whereas relative lowering of vapor pressure is of, look at it, colligative property. Okay, you have to remember this. Lowering of vapor pressure is not a colligative property, whereas relative lowering of vapor pressure is a colligative property. Now, from this particular expression, we can determine the molecular mass of the solid particle. So, we have determination of molecular mass. Determination of molecular mass of the solid. Now the numerical will be asked from this particular section. So M2 will be equal to P0 by P0 minus P into, we have W2 by W1 into M1. So from this particular expression, you can determine the molecular mass of the molecular weight or the molecular mass of this particular solid particle. 2 is for solid, please don't forget, and 1 is for solvent. 1 is for solvent. And by knowing its relative lowering of vapor pressure, we can determine its molecular mass. It means solid, molecular mass of solid. Let me write W1 and W2 are W1 and 1 is for solvent. Okay? W1 and M1 are the weight, weight and molecular weight. Molecular weight or mass of solvent. And W1 and W2 and M2 are the weight and molecular weight of solid. This part we have to remember it properly, of the solid. So from here the numerical will be asked. So this is the end of today's class. Thank you.